So today we have a very interesting conference titled Mitigation Landscaping Affecting Highway 40 North of Grande Cache, 3 sites with different solutions. So in this conference, we are going to review the experience of Thurber. Thurber has been participating in Alberta Transportation Geohazard Risk Assessment Program for many years. This presentation describes 3 sites along Highway 40 located north of Grande Cache, where remedial measurements were carried out to stabilize sections of the highway that were being affected by landslides movement. The 3 sites were chosen to demonstrate a variety of techniques that were implemented, ranging from lob flattening, offloading, to constraint investigation, ranging from slope flattering, offloading, to dewatering, excavation and replacement with a strong backfill, shear keys, to beams and pile walks. The site conditions, constraint, investigation, design, and construction are touched on each site. The goal of the presentation is to provide a toolkit of techniques of various remedial projects. So to provide that toolkit, we have with us today the engineer Don Proudfoot. He is a senior geotechnical engineer and partner of Thurber Engineering. He completed his civil technologies diploma at NAID and then joined Thurber in 1980, taking breaks to complete a bachelor engineer in civil engineering at Lakehead University and then a master engineering degree in geotechnical engineering at the University of Alberta. He has spent a 4-year stint helped open a Thurber office on Toronto, but has otherwise worked out of the Edmonton office. Dom is married with 3 children and loves anything that do with the outdoor. Dom spend a lot of time assessing, investigating, and remediating landslides that are affecting Alberta's highway, which is what this presentation will be focused on. So please join me in welcome Dom today. Thank you.
Thank you for the nice introduction, and thank you all for having me here. I'm going to speak about something I really enjoy, and that is working on geohazards. So as mentioned, I've been involved in the geohazard work for Alberta Transportation for a very long time. And as part of that project, we get a chance to go and look at different hazards that are affecting the highways in Alberta. And we get to investigate, figure out what's going on, come up with options for fixing them, and then go out and implement some of those options in the design and construction. So what I'm going to talk to you about today are 3 landslide projects that we worked on Highway 40 between Grande Cache and Grande Prairie. Also, I'd just point out we have Nicole Wilder sitting here. She's worked on all these projects with me. So if I get stuck on any questions, I'll be pointing to her. Good. Okay, so let me begin. So, okay, we'll just do that.
Mm-hmm. Oh. No, wait.
Just have to start it.
Yeah. Wait, what we did was.
There we go. Okay. So this is a map that kind of shows you where the sites are. So Alberta Transportation, they have a numbering system so they can track all of their geohazard sites. So that the highway that I'm talking about is Highway 40, and it goes from Grande Cache up to Grande Prairie. South of here, it would go down to Hinton. The 3 sites I want to talk about are GP 006B at this location, GP 042, and GP 034. So the highway along these sites runs along the Smoky River, sort of parallel to the Smoky River along a side hill in the foothills of Alberta. and then it crosses overland and then comes down into the Kakwa River Valley. So that's where these geohazards are located. A few other things of interest here are Sheep Creek Pit. This is a gravel pit that Alberta Transportation operates, and we were using that as a place to get rid of some material that we took off some of the sites. And then further up is Teddy Lane. So this whole area up here has a lot of oil and gas exploration activity. And Teddy Lane is kind of a big developed area with lots of housing, and that area was used for a big stockpile from a road widening project that happened here. So we used some of that material for one of the landslide repairs. So I'm going to talk about the 3 sites and some of the techniques that we looked at for fixing these sites, ranging from drainage to slope offloading, shear keys and pile walls, and toe berms. Okay, so the first site here, this is a satellite image of the site, and okay, so this is where the landslide was affecting the highway, and here's the Smoky River. And CN has railway tracks, and then we have an embankment that goes up to the highway, and then this slope goes up the foothills of the mountains here. So this is a landslide that was affecting the highway that was built on a side hill alignment. So the left side of the highway is cut into the slope. The right side is an embankment fill. There's a steep hillside slope upside of the highway. And on the other side, there's a high fill that goes right down to railway tracks and some utilities. So the toe of the slope was constrained by a bunch of things that affected the solutions we could use. So there's a bunch of pipelines, an overhead high voltage power line, and some railway tracks. So here's a picture of the site about a year before things started really moving. It was a site that Alberta Transportation were keeping an eye on. You can see there's some cracks in the road, and there were some slow creep movements in the highway. So they were keeping an eye on it. They had some instruments installed and monitoring. But we had a couple of years of very wet weather, and this site was affected by rise in groundwater levels, and things started to move all of a sudden. So this is what the site looked like in 2019. And along the highway, there's a bunch of cracks here, and the highway started to drop fairly suddenly. This also gives you an idea of the slope coming down. Here's the high voltage power line, and there's the railway tracks and a bunch of pipelines buried here. Here's another drone shot just looking towards the landslide that was up in here, and the Smoky River along there. So in May 2020, the movements really started to go, and they started to tear the highway apart. And Alberta Transportation had to block off part of the road and build a bit of a gravel detour on the other side to keep traffic going through while we came up with some solutions to fix this problem. We did some geotechnical investigation to supplement some of the existing instruments that were there and previous testable information. We installed some piezometers to measure groundwater pressures, and we installed some slope inclinometers to measure ground movements. This is just a map of the area. All these little targets are the boreholes that we had. SI would be the slope inclinometers, and VW would be vibrating wire piezometers, or there were some older pneumatic piezometers and sandpipes. But we looked in the area of the landslide cracking here, but we also looked a little further north and south in case we wanted to do a highway realignment. And here's a typical cross section of what we found there. So it was typically some soil and embankment fill over here over bedrock that was layered siltstone and shale. These numbers here are SBT N values. So the lower numbers are, kind of firm to stiff material, but once you get into the bedrock, in soil terms, you'd call it very hard. We also, these are like the screens in the sand pipes, and that would be the water level that we measured. And here, these are the vibrating wire piezometers, tips, and the water level at that tip location. And so here's the slope coming down, and then at the bottom of the slope, we had an abandoned gas line, but we had to treat it as if it was active. So this kind of eliminated the option of putting a tow berm, and that would have been the simplest, least costly option, but we got pipeline here, a few more pipelines in here, and overhead power line, so we couldn't do that. So another option we thought about was a pile wall here. We could put piles in to hold the highway back, but that one was considered a bit too expensive. So we ended up looking at the measures I'm going to explain to you here in a minute. First, I'll show you the instruments. So these are some piezometers. As I mentioned, they were being monitored for a number of years prior to the big movement. But when the big movement occurred, it was during some very wet weather years, and the pore pressures rose. And these are in meters of head, or certain meters below ground, but they'd be the same as meters in head. And you can see that when the movement started to occur, the groundwater table had come up, and it kind of destabilized the area. So that was kind of a cue to us that we should think about dewatering this site. It's probably going to be something that's going to help stabilize. This is one of the slope inclinometers that was installed within the landslide area on the shoulder of the road. And basically, I don't know if you know what those are. They're basically a tube in the ground, and you put a sensitive probe down, and the first time, and you read it at intervals, and it has accelerometers in it that track the alignment to the pipe. So the first time you call it to 0 and it's a straight line, and then you read it at intervals at the same low depths, and you can see if things are moving down there. And so for several readings, not much was happening, but then when we started getting those high groundwater levels, the ground started to shift. And so it was shifting in this zone about 7 meters below ground surface, which we'd call the shear plane. And so from an incremental movement, we get this kind of movements of, 70 millimeters, but the deformed shape of the pipe would look like this. So the top part is moving in the landslide. So what we ended up, we looked at several options. We always do that for Alberta Transportation. They've got to come up with the most economical option that fits the conditions. But this is what we ended up coming up with as kind of the best fit for this site. So we did a combination of things. One was we offloaded the top of the slope where the driving force on the landslide. And to do that, we ended up building a bin wall with 60 bins, 180 meters long, and about 3.5 meters high, plus another sloping ground of fill of 1.5. So a total height of about 5 meters for the wall. And that allowed us to take soil off the landslide just on the downslope side of the wall. Behind the wall, we dug out the landslide mass and replaced it with stronger gravel and put some drains in there. We installed subdrains below the ditch to intercept these water, the seepage, so that we can control it during the high weather periods. And then at the toe of the slope, we went down with a drill rig and we installed some sub-horizontal drains to get deeper into the ground and intercept the water. Now, all of these things cost about $3 million. I'll give you a rough cost for different things so you can see what this toolkit costs. So we did some slope stability analysis. This is just slope W here, but we're showing this black line here was the original ground, and this drop off is where the bin wall was installed. And then these two black lines are the horizontal drains, sub-horizontal drains, and below the ditch we put another drain. So that combination there, we were shooting for a factor of safety of 1.3. So AT, Alberta Transportation, they typically look for 1.3 for a highway and embankment. And if you've got something like a bridge or a structure, they would like 1.5. So our target value is 1.3 here. And this combination of measures would achieve that. So here's an example. Here's the design drawings that we came up with. So we put a subdrain in the upslope ditch there, and it had a manhole to access it, and then it would drain out down here further down the hill into the ditch. The bin wall is this dashed hatched line here. So a bin wall is basically boxes filled with gravel, metal boxes filled with gravel. And then we offloaded this part of the slope by cutting out a bench. And then these are the sub-horizontal drains. So they were drilled from down below into the ground at 2 different levels to intercept water. And that combination made up the design. You can see all the various things. There's a bunch of, there was a gas line here that we had to locate to make sure we didn't hit it with our drains. We had to stay far enough away from the overhead power line so that it didn't electrocute anyone. And then of course the CN was concerned too. They didn't want stuff coming down the hill and hitting their trains as they went by. So we had to keep that in mind. So here's a cross section of the design measures. Bin wall with the gravel behind it, the drain here, and then these are the horizontal drains. And to do them, we had to cut a notch into the toe of the slope to get the drill rig so it could drill into a face here. And these are the 2 inclinations that we did to tap water. And then there's that overhead power line and trucks. So a few pictures from construction. This is the bin wall being constructed. The bench has already been cut. So we first unloaded the slope before building the wall. And at the same time, they were starting some drainage down above and below. So this is the subdrain going into the ditch. So the subdrain is a perforated pipe, and we surround it with a filter material, which is like a washed rock, gap graded rock. And then we surround it with non-woven geotextile to filter the water coming in. So this was installed at about 3.5 meter depth along the highway here to lower the water table there. And this is how you install those drains at the bottom of the hill. So this is a branch of Mobile Augers. They're one of the local drilling companies. They have this aardvark drill here, which can drill it horizontally and at angles into the ground. So to do that, you've got to cut a notch here to get it going, and you got to align. So this is one drain that was installed already, this white pipe. So they drill with a disposable bit. So this was drilled with water and like a tricone type bit. You get to your target depth, and then you knock the bit off. You slide like the drain pipe in through the middle of the pipe, you knock the bit off, and then you remove the steel pipe, and you're left with this in a hole. And you do use a lot of drilling water. So one of the constraints here was we were near a river. We couldn't let dirty water go out and get in the river. So they dug a temporary sump, and then they sucked this into a water purifying system. And then later, when these were done, we came in backfilled with gravel and then put some riprap to bring the water out to disperse on the ground here. This is an example of how they dealt with the drill water. So it would first come, they would mix it with a flocculant in a tank here and settle out some of the coarser particles. And then they transferred it here where it went through a series of jute matting and that to further clean it. And they had a specialty contractor on site for that. And they had environmental people monitoring turbidity of the water. And once it was clean enough, we could then send it back to the river. Well, they sent it to the forest to disperse in the vegetation by the river. So here's some pictures of the finished job. So this is the edge of the bin wall. 1.5 meter high gravel fill coming back up. This is a little asphalt curb to keep road water from going over the wall. We brought it back to a swale. Had to put a guardrail in there to protect traffic from falling over the wall. This is the bench where we took material out below the wall, and you can see the tracks in the bottom. This is the bottom. These are those drains, and quite a few of them had steady water coming out of them. So we know that they're lowering the water table, and it's pooling in this area here. And you can see the bin wall up above. So that's pretty much it for the first site. I would say that the material we dug out of there, we had to put somewhere. We couldn't leave it down here. So we took it to that gravel pit further up the road, and we put it in there. So this one was mainly a drainage and a slope offloading solution. The next site I'm going to talk about is still under construction. I'm going to just show you a few parts of it. This one is north of Winiandi. It's further down the highway towards Grand Prairie. And here's a satellite image of this guy. So it's further up the valley from the Smoky River, and this is a fairly steep valley that goes all the way up, and then it keeps going up many meters further up the hill. So it's quite a big site. We have one landslide down here that I'm going to talk about. This is kilometer 37.6. And then there's a few slides affecting the side of the road here where we did some pile walls. This material downslope here is all in a state of creeping. It's old landslide material it's forested, but it creeps down towards the river. So this is another site where we can't put a toe berm. Really, you'd be putting a berm on top of moving soil, and you could make it worse. So I kind of summarized this. It's similar. It's built on a side hill. Lots of water coming out of the slope. We have landslides that are almost a kilometer long along the highway, and some are into the highway and some cracks are just down slope of it. There was an old bin wall there already that they had built during the construction of the highway. The landslide was coming near the bottom of it, so we were worried about this becoming destabilized. We know there were some subdrains installed in the whole hillside before when they built the highway, but there was no good records of it. So we did our best to find some of the drains and put the pieces together, but we didn't have a nice map of where they were. So here's a few photos. So this is looking south. You can see the Smoky River down here. So we're quite a bit higher above the river than the last site. This is the bin wall I was talking about. So, and this down here is at that little kilometer 37.6 slide. And you can see the top of the landslide here, and then it goes around below the wall, comes up here, and it kind of follows along here. So this is what we call the back scarp of the landslide, and this is the moving mass that's going down the valley. Just another view, you can see a better look. We're looking the other direction at the wall, and here you can see the cracks of the landslide that are coming up into the highway here and close to the highway down here. This is the slide at the south end of the site. It's what we would call the, oh, sorry, someone's looking to get admitted. Are you doing that, or do I need to, you got it? Okay. Okay. So this is what we call the kilometer 37.6 slide. It was a more local, smaller slide, but it was going all the way down the valley. And this picture was taken at a time when it was further from the highway. It eventually went in and actually destroyed part of the highway. Yeah. So this is what happened when it moved into the highway. The highway, this part fell and started moving away, and we have a gap here of about half a meter drop on the highway. So of course they had to close that part of the highway and move traffic around in the ditch on a temporary basis until something was repaired. This is the big landslide below the bin wall. So this is the scarp of it. And if you take geology courses, you've heard of grabens. So this is the main crack, but this is another crack. And as it moves, this piece of ground drops and creates a dip. But so we were worried about this. It's only 1 meter to 2 meters away from the wall. And if this undermines the wall, then the wall can fall over. So I had to come up with a way to stabilize that. So I'm going to talk first about the smaller slide, the kilometer 37.6, is I want to demonstrate a shear key. So the solution we came up for that, because the bedrock was within a reasonable depth to excavate out the landslide, we just dug out the landslide and we rebuilt it with gravel, and we dug everything down to the bedrock. So we had a firm base to build on. And while doing that, we put some drains in and restored the pavement, and this one cost about $0.6 million. And here is a design excavation plan for the landslides, for the repairs. So this is the landslide came up the dashed lines and into the highway. So we basically dug out beyond it into the road and beyond the sides, down to bedrock, and we put a shear key in there and a drain like a horseshoe all the way around, and then drain the water off down onto the slope. This is what it looks like in cross-section view. So we again put a subdrain on the upslope ditch through the whole length of the project to catch water there. We also put one in this excavation. And so we had a bunch of soil and colluvium on top of interlayered bedrock with shale, sandstone, and siltstone, and a bit of coal in some places. So the idea was to dig out. This is the landslide here. This is our interpretation of where the landslide bottom is. So we dug below it down to the bedrock, and here we put a shear key into harder bedrock to make sure we got all the weak material out, and then backfilled it all with gravel. This is the excavation, and you can kind of see the soil conditions along here. This is some of the landslide material that was moving on top of the bedrock. When we dug out the weaker weather material, we found bentonite in there. It's kind of this yellowish stuff, and bentonite's very weak material. You can get like friction angles of 6 to 8 degrees in it. So that material was removed from the bottom of the excavation before we backfilled any gravel there. This here is the shear key being dug. So we're putting it into more intact bedrock just as an extra defense. So like in your stability runs, we want to make sure that we're forcing the slip surface of a potential slide through the gravel to get our factor safety where we need it. Construction going on. So now they're backfilling the gravel in layers. This black material is the gravel that was crushed strong bedrock from a quarry down by Grande Cache. And they're building it back in layers up to the road level. And it's in place. We then put a clay cap and topsoil on top of it so we can get grass growing. And then these are erosion control coverings. This one is a straw coconut type matting, and this is a more permanent TRM. So we cover them with these after we seed the topsoil. We can get better grass growth going, and eventually a guardrail goes along here to protect the traffic as well, and that's where our drain comes out here. So that's the shear key job. For the rest of them, we couldn't do a shear key. The bedrock was too variable, and we would have had to tear up the road too much. So we used pile walls. So we actually did 3 pile walls, and they were to retain the shoulder of the road and the bin wall. And these pile walls had a total length of 257 meters. They consisted of drilled reinforced concrete piles, and they were socketed into the bedrock. So we had 110 piles that were 1.2 meter diameter and 83 that were 1.5 meter diameter. And over each of the 3 walls, a whaler or a cap beam was built to tie the piles together so that they would act integrally instead of as individual piles. So you get a stronger wall that way. And then there's one section that the bedrock was fairly deep. So at that one, we also used tieback anchors, so ground anchors. So you drill in and you anchor these steel rods into the bedrock behind the landslide. So they were 32 meters long, and we used 58 of those. This system was designed, we knew that the landslide would keep moving downslope of the wall. So it was designed to lose that support. And the total cost of the walls alone was about $8 million. So they're fairly expensive, but they certainly have their purpose in a site like this. So this is a plan view of 2 of the walls. Wall 1 is the one where we did some tiebacks in the deepest zone here of the landslide. Wall 2 is we overlapped, it was further down the slope from the highway. That's the highway. It was overlapped with 1, and it goes beyond the bin wall down here too, so that we can protect the bin wall. And then we did some slope or grading above the walls, put drains behind them. These are several boreholes that were drilled on the site to investigate for the design, and we put instruments in them as well. That other site that I showed you is further down here off the page, where the bedrock was a little shallower. And the back slope, which was also moving, was cut back and some drains were put in that. But I was just going to focus on the walls for this site. So this is wall one. It's where it's maybe a little hard for you to see, but this borehole here is soil that would be described as clay till. It's likely colluvium stuff that's come down the hill from weathering of the mountain. And it sits on bedrock that's this interbedded shale, siltstone and sandstone. So the idea was, and the slip surface of the slide was inferred to be along the contact between the soil and the bedrock. So these are N values from a standard penetration test. And then we drilled with augers till we got auger refusal, and then we used an air percussion type system called Odex for getting into the bedrock. Here's our piezometers, and so the slide that's moving in here, it's kind of moving like this at that level. So you need to socket the piles well below the top of the bedrock so that we can provide enough of an anchor here to prevent the wall tipping. And in this case, we needed extra support from some tied back anchors. So you drill them past the slide zone. So up here, the soil kind of comes down across like this. So we put these bond zones for the anchors beyond that in the rock. And each of them were 12 meters long. And we had up to 2 rows of anchors, one through the whaler and one cord through the piles. And then with ground anchors, you anchor them somewhere that's not going to move and that's strong, and you have to put them behind the active earth zone of the active earth pressure zone so they don't get affected by movements as the system tightens up. So that's why we got to put them back here. We have a free stress zone, so once they're installed, you actually pull on these steel, high strength steel tendons, and you pull on them until you lock a load off in the wall up here. And that imparts you use the soil resistance in this grouted section here to provide that resistance. So the other part of this was this subdrain in the ditch. And then these are trench drains that were put up the slope after we cut it back. So that's the whole system. And we cut a little bench below the wall to take a little soil off. We needed it for access anyways to install these anchors. Here's just another stability run with the anchors in and the pile element here. And this is the local stability. So we have assumed that we're going to lose all the landslide material. It's going to take off down the hill. We want to make sure this wall still can stand if that happens. So, and then these are piezometric conditions that we're modeling here. And we're assuming that if the soil leaves, that some of the water will drain down here and down. And then this is the lower piezometric level in the bedrock. So we have to convert this all to some sort of an earth pressure diagram to design the wall. And so we've converted the landslide pressures into an equivalent trapezoidal section. You put a traffic surcharge on the road here to simulate trucks driving by. These are the anchors here. And then we're assuming we're getting no resistance from the landslide mass. Here's the top of the bedrock. So the top of the bedrock was a little weathered. So we discounted some of the strength up there. But here's the soil resistance here. And these are spring values that we need in the structural analysis. So then we handed this over to a structural design firm, Dialogue, that did this for us, and they set up a model, and they apply the loads and they put the resistances, and we tell them how much this wall is allowed to move. And for a tied back wall, you don't want it to move more than about an inch. If it's a cantilever wall like the next one I'll show you, they can move more than that. So this is the other wall. This is wall 2. There's the bin wall. The bedrock, this is our slip surface. So good rock below it and moving landslide here. So we use larger diameter piles, but no anchors. We were able to make this work as a cantilever pile wall. So again, you've got to come back and say, what can everything tolerate? And I can't remember what kind of allowable pile head deflection we said. It was 50 to 80 millimeters. And so they would model this and limit. And it's often the deflection that limits your design. Here's a stability run. So we check all kinds of things here. So, you know, we want to make sure that the primary thing is to protect the highway. We also want to see that, you know, the pile wall is going to support it and get our factor safety 1.3. So here's an equivalent load diagram for this wall, where we're converting, you know, a trapezoidal type pressure for the bin wall and the traffic against the whaler, discounting the soil that will leave. But because there's a shallower depth to the intact material, we can get away with a cantilever wall, but we need stronger piles to make it work. So a few pictures of construction. So you have to figure out how to build this. So you're on a landslide, and you got to tell a contractor to go out there and put his equipment on a landslide and install your piles. So we usually have a bunch of guidelines for them, like rules that he has to abide by. We usually start at one end of the wall and we work our way into the middle so the piles don't break from a landslide movement before you finish your job. We limit how much the bench can be. They need a certain bench here to have enough room to get their equipment on. So we usually let them cut a bit and fill a bit, but we put limits so we're not overloading the landslide. And here they are. So this was Keller that worked on this, and they drilled these piles, and they needed a variety of tools. You're going through till with boulders in it like this, and then you get to the bedrock and you need sometimes core barrels and carbide teeth to get through the hard rock. And in fact, some of the rock was fairly hard, so they actually used a smaller diameter auger to pre-bore, and then they used a bigger one to ream it. So here's all the rebar. Quite a bit of rebar goes into these piles to get you the shear resistance you need. This is a view of the other wall, the first wall with the tieback anchors. So you can see a rig putting in the anchor, so they also have to sit on a bench. He's doing the second row of anchors here through the pile. So we core a hole through the concrete and we drill through that. The first row of anchors in the whaler, we actually had them form a sleeve in the whaler so that they could just drill through the preformed hole. And so these go back 32 meters from the face of the concrete wall. And then we lock them off against steel plates on the wall, and that becomes your permanent thing. Every anchor is tested. So before we get into production, we have the contractor do a pre-production test, and they install an anchor and they cycle it, load it, and they take it. I think we went a couple times above the design load, and we didn't fail the anchor. So you either want to fail it or take it to at least a couple times the design load so that you know that your design strength is available. And so you do that first, and then once you're actually building them, every production anchor is tested. So we do two kinds of tests. We do a performance test and a proof test. A performance test is a little more involved, and you cycle and you hold your loads and you step it up to 1.3 times the design load, and then you step it down and you make sure your anchor's not creeping and that the free stress zone is extending the way you want it to. And the proof test is just a quicker version of that. So, but every anchor gets tested, and you can see they have a green jack here that slides over the bar, and you stress that to pull on the rod. And then you have a dial gauge here to measure the deflection. And then we have a load cell in there to measure the load. And they also have a pressure gauge on the jack that they apply the load to the jack with. So we plot up a curve for that, and we make sure everything is within the criteria we have. And then we accept the anchor and lock it off. And here's a picture of the wall. They're going to come back in the spring and finish the fine tuning, but this is that wall with all the anchors in. This is the ground line. They're still backfilling around it, and there's a drain behind it. And we do have instruments in the wall too. We've installed an SAA, it's a shape Excel array, it's called. And we've installed some load cells. So the shape Excel array is like an electronic slope inclinometer. You can hook it up to a data logger and you can monitor movements on it. And so we do have a data logger being installed out on site right now. And then we have load cells on certain anchors here so that we can monitor the load over time. So this site will be monitored for many years, and this is just a way of checking the health of the wall. Okay, so that concludes that site. And then I'm going to take you to the last site here. This one is by the Kakwa River. And we're coming down a hill into the valley of the Kakwa River. And there is a landslide happening here on the side of the road. And you can see this here is the embankment fill. And again, it's on a zone where we have historic landslide movement. And this is a view from bare earth LiDAR. So we geotech people love LiDAR. It's basically strips the trees off the ground and you get to see what the ground looks like. And if we shade this for different degrees of steepness, we can get an idea of where the steeper portions are. So the steeper portions are blacker, the flatter portions are lighter or whiter. And from that, we can tell if we've got a landslide in a valley slope. And so we've dashed, this dashed blue line kind of shows the extent of the historic landslides. This red line shows the extent of the recent landslides. And we feel proof that by inspecting it for a bunch of years, we could actually see the cracks and the movements. And for this, yeah, so I'll just take you to the next photo here. So this was another site where we have the road on a side hill. There was movement in clay under a previous embankment fill. So they had built an embankment. During construction, they had some problems. They had to fix them and they got it built. But then years later, it started moving again. And this is where we came in. It's on a steep hillside upslope of the highway, and there's quite a bit of high groundwater in this area. Here's the site plan. We had, this is the embankment fill, this is where the landslide started affecting the road. These are boreholes. And we had seepage coming out of the toe of the embankment fill down here, and the ditch was very wet. And this is what it looked like when it started moving. So side of the highway started dropping, and of course you got an unsafe condition for traffic. So some more cross sections, but basically it was moving through the fill and coming out the bottom. So on this one, we used a combination of a tow berm and some drainage, and it cost about 4 million. And so here's the outline of the tow berm. We put some French drains in to help collect water downslope of the berm and under the berm. And we put a drain along the top of the highway. And here's a cross section design with the tow berm and the drain under it. And here's the drain under the ditch. Here they're digging in the French drains, filling them with gravel. Here's the ditch drain with the outlet of the pipe. Here's the drain going in with pipe and the washed rock. A tow berm being built, and it's quite a massive tow berm. So one of the things we worry about with putting a load on a slope is pore pressures. When you analyze a job, you should be looking at the short-term undrained condition and the long-term drain condition. So with all this weight of fill that we were putting on top of the tow berm, we did have instruments installed that we could monitor pore pressures, and we had some slope inclinometers. So the slope inclinometers had shown where the slide was moving before construction, in this zone. And by reading it at intervals during construction and during the slide event, we could see what was going on. So initially it was moving along like this, and then it started taking off and the rate of movement really increased. And then once the tow berm was on and left alone for a while, it started to decrease and stabilize. So you have to be careful that you don't make things worse while you're trying to make them better. So the tow berm is going to make it better in the long term, but in the short term, when you're building up this pressure, you're putting a lot of weight on clay. It squeezes the clay and the water can't get out. So it builds up pore pressure and it floats the material and makes it want to move. So we often use an observational approach when we're building these to make sure that we don't fail something during construction. And we were starting to get a little nervous about this one. The pore pressure started jumping up quite high, and they were getting a little higher than what we expected. So we made a decision with Alberta Transportation to make the berm a little less high. Like we stopped building the last 2 meters and just topped it off. This is how the berm ended up. So the final berm, and it's been performing pretty good. Like something like this always takes a while to tighten up. Like with the walls, things happen pretty quickly. With a tow berm, you got to give it a few years to tighten up. So there were some continued slow movements after construction, but things are settling down now in there. So that takes me to the end of the talk. I just want to make some acknowledgements here. The owner of all these projects, Alberta Transportation, that we've worked with, and these are some of the key people that we deal with on the projects. Thurber, we've had a number of people involved in the job. As I mentioned, Nicole was working on the designs and managing the jobs, and we had a number of different inspectors out on site making sure it was built properly. And our sub-consultants were Dialogue for the structural work and WSP for the survey work. And these are the contractors for the 3 projects. Ledcor was the prime for the first project, and these are their subs. Mardashev is the one doing the pile wall job with Keller and Double Star on the anchors. And then this last tow berm one was Wapiti Gravel Suppliers, and Prairie North did the grading work for them. And that's it for my talk.
So thank you very much, Engineer Proudfoot. Now we have some time for questions. We are going to do as usual, some questions here in the room and some questions from the people online. So there is any question here in the room? Okay, give me a moment. Oh, it's right there.
I have a couple of just start off more and else online and then chat faster. Just to do with one of the last comments that you had in this last site here. How much displacement did you actually see before the situation tightened up?
Like after we built the thing, it did set. That's okay. So like you can think about it, you've got a moving mass of soil and you're putting a weight on it to try and stop it, but it's a momentum thing. You have to slow it down and stop it. And we probably saw another 50 millimeters of movement. We actually sheared off the SIs that are in the slide mass. That's why that last one hadn't leveled off nicely. But what we're using to monitor it was the deformation at the surface of the road. And so it came down another maybe 20 millimeters or so. They were planning an overlay job, so we had advised them to hold off on the overlay for a little while to patch it. And if it moves a bit more, they'll have to patch it just to keep it even. But,
It's a bit bigger, yeah, it's flexible system. That's why it's
yeah. Yeah.
Thank you.
No, oh, no, thanks. Yeah.
And now, hopefully you can I'm going to present the questions that are online so you can all see them. Gosh, it's going to.
Should mention all these sites we continue, AT continues to monitor them until they're comfortable, everything's great, and then they kind of take them off their list.
Are you watching the questions? I have like a bunch of questions here. I'm sharing my screen too. Yeah. I have to share my screen one. Oh.
Yeah, okay.
Yeah, I guess that will be the best idea.
Okay.
Okay. So, okay, so we have our first question is from Vincent Hound, and it's what happened in case where the anchors do not meet the test load or performance requirements? Is this a design risk that we owners accept or a construction risk for the constructor to resolve?
Okay, so no, that's a good question. So when we're putting the designs together, it's based on some of our analysis and experience. So we're pretty certain that it's going to meet when we do it, but we always do double check to make sure it does. So there are a few possible ways of mitigating this if it doesn't. One is that we can increase the number of anchors, which would be a little awkward if you've got a design already, but that's a solution. If your anchor came in, if your test came in a little lower than expected, you could add some more anchors into the design. You could lengthen them, although we've kind of picked the optimum bond zone length of about 12 meters. Based on our experience, that's about the right length where you're getting the maximum resistance out of your anchor zone. There are other methods you can do in the field. If you almost make it, or if you're into production and one doesn't quite make it, you can post grout the anchor. So, and these were all post groutable anchors. So I didn't mention that, but we put little tubes down the sides of the anchors with ports. And after you've done the initial tremie grout, if it's creeping a bit too much, you can inject some more grout under pressure, and it cracks the bond and the soil, and it makes the bond bigger, and you can get higher strength from that. And you can post grout a couple of times if you need to. So on every job, there's usually 1 or 2 anchors where you had a few installation difficulties. You can post grout to get that extra strength on those.
Okay, perfect. Thank you. Any question here? Can we continue? Okay. From your experience, is SAA better than SSI? If access wasn't an issue and remote reads were required, will you still prefer SAA?
Okay, that's from Anna. Yeah, I know Anna. So the thing we like about the SAA, I guess, is it gives us a continuous profile and we can read it frequently. We're trying to, we have a number of these pile walls in the Peace region for AT. We're trying to have them all instrumented, and in fact, in many cases put modems so we can dial up and get the readings so people don't have to go out to get them. We still rely on the SIs a lot, and I guess they're a lot cheaper than an SAA to install. And in fact, we have SIs in the wall at that project. We just put the SAA in one critical pile in the most critical section. More of a money thing. Like the SAA, it's like $30,000 for the SAA versus a few $1,000s for the SI. But you end up spending more time reading the SIs than the SAAs. So I always like to have an SAA when I can, but it's usually quite expensive. So we have to kind of balance the desire with the need. If you had a project where you're where it's critical to pick up movements on an ongoing basis, I would prefer the SAA for sure.
Okay, Hussein Rinani asks, how was the group reduction factor of 0.44 it was determined for the piles?
Okay, with piles, piles adjacent to each other impact the kind of resistance you can get from the soil. I guess if you had a continuous sheet pile wall, they're right together, and you would use like an active earth pressure or a passive earth pressure. If you have a single pile standing by itself, you can get 3 times the resistance because of the arching effects, and it's affecting the ground for a certain distance from it. But in our case, we usually our stuff is kind of based on Berms theory, where we went from the reduction factors that he recommends, and as you're pulling them closer, like if you're more than 4 diameters apart, we usually don't reduce this from the 3 times strength. As you're pulling it closer together, you start reducing them down to where you'd have the continuous like passive earth pressure resistance.
Okay, right. Also, Hussein asked regarding the proof and performance of testing of anchors. It is usually done on a percentage of anchors. Any reason it was done on all anchors in these projects?
Yes. Yeah, so we do a proof test on every single anchor to make sure that it's going to perform as needed. You know, you do have difficulties with some of the anchors, and the proof test is a pretty quick test. It usually takes about 15 minutes. The performance test, we usually pick about 10% of the anchors, and that's one where you cycle more cycles up and down and you hold the loads longer. And we usually kind of pick it in different sections of the wall just to make sure everything's working the way we want it. But on all of our pile wall jobs, we've always done at least a proof test on every single anchor, and it just gives you that assurance that the system's going to work properly.
Is there any question in the room? Okay, so we have the time for a last question. It will be the ones from Lynn. It says, for the wall where it was assumed that the material down slope will continue to slide and not provide support, did you completely eliminate support from that material, or do you allow it for some temporary support?
So that's a good question, Leon, and that really depends on the site that we're on. At this wall site where we're doing the pile walls, we have a fairly long continuous slope. We know that the soil is moving, we can see it moving there, so we did not feel comfortable on relying on any of the support. And if you relied on the temporary support, then at some time you got to come back in and account for it if it moved too far. So usually where we can, we will design the wall in this scenario to assume that there's going to be no support, and it's a wall that we don't have to worry about. We have had a few projects for Alberta transportation where a decision was made that we are going to count on some of that passive resistance from the soil, and we're going to monitor the wall, and we're going to have more instruments in it. Sometimes we actually put an SAA in the slope, in the soil down slope of the wall, so we can monitor how it's moving relative to the wall. And we check load cells, and we have some guidelines as to when we might have to come and intervene and put another row of anchors in. But when you take that approach, you're saving money up front, but you might be spending it 10 years down the road later. And we do have a couple of sites like that where we're using that approach to save some money up front.
Okay. So thank you very much, Engineer Don, and thank you everyone for attending our seminar today. You are welcome next Wednesday with the presentation Best Mine Lake, the first full-scale pit lake in the oil sands. Thank you very much.
You all for attending. Yeah.